Deepak?
Yes, sir.
Are we starting now in a minute or so? Will you be?
Yeah,
Okay.
Yes, in a minute. Okay. Narayan sir, can you let the people in the waiting room in?
Done.
Okay, shall we begin?
Yeah.
Good morning, everyone. Today is the first session of the online school children's program. Yes, sir.
Yes. Should I take over?
Okay,
now?
in a minute. Yeah, I'm just giving the speech and I'll hand it over to you. Yeah. So, welcome.
Hello. Hello.
Yeah. So, okay, we'll begin the session. Mani sir, you want to start?
Okay. Good morning, everybody. We are starting this program, and I have requested our director, Professor Madhav Mukund, to start this series for this academic year. Professor Madhav Mukund.
Thank you, Professor Mani. So, on behalf of CMI, we are very pleased and proud to co-host these outreach talks for school children in association with the National Academy of Sciences. So in previous years, we have been doing it on our campus, and we have had over 100 students and a comparable number of teachers coming to our campus for 2 days for these talks in subjects ranging from maths to physics to computer science. Unfortunately, last year and this year, we have not been able to host this on campus, but in a way, it has been an advantage because now we are able to reach a much larger audience, not just those whom we can accommodate on one day on our campus. So that kind of turns it into a slight blessing, even though it would be much nicer for us to host you. Just a little bit of background about the institute. So I'm sure that many of you have heard about it, but CMI is an institute which combines research and teaching at the highest level. So the focus is on the mathematical sciences. So we have BSc programs in mathematics, computer science, and mathematics and physics. And we go on to have MSc programs in mathematics, computer science, and now recently in data science. And of course, we have always had a research focus. So right from the beginning of our starting time of the institute, we've had PhD programs in maths and computer science, and more recently in physics. So the campus is compact. The number of students is not very large. We have about 250 bachelor's and master's students and about 50 PhD students. But at the same time, it's very active. And a lot of the people on campus who are even the conventional courses in BSc and MSc are engaged in talking to people who are doing research. So we have a very strong research culture in our campus, and that reflects the fact that many of our students actually go on to do PhDs, and quite a few of them are now faculty members in many institutions in the country like IITs and IISc and so on. So this is the context of our involvement in this, which is that we would definitely like, along with NASI, try to get more talented students like all of you to be interested in taking up careers in science and mathematics. So through these talks, we hope to incite you and interest you to take up these subjects more seriously as you progress in your studies. And with that, I would like to hand it back to Professor Mani, and I'm sure all of you and all of us are looking forward to an extremely engaging series of talks today and in this whole series this year. Thank you.
Now it's a pleasure to welcome Sivakumar, who is teaching at Krea University. He did his PhD in IIT Madras in quantum optics, and then spent some time in IGCAR, in fact, a lot of time. After that, he moved for a short while to Chennai Mathematical Institute, and then is now professor and developing the departments and Krea University, Sri City, Andhra Pradesh. So he's going to talk to us on Pick's theorem today. So I request Dr. Sivakumar to please start the talk. Thank you.
Sivakumar sir, you can go ahead.
Yes. Is it visible now, Deepak?
Yes, sir.
Good morning. Let me first thank Professor Mani and Professor Madhavan Mukund for the invitation. It's always a pleasure to talk to students. And today's topic, in my opinion, is very, very accessible to school students. It is possible to sort of understand why we can expect this result to be true, and then actually prove that it is true. So these are the two parts that are usually involved in research. So you gather some ideas which sort of tell you that this could possibly be true. Then you construct a rigorous proof. Of course, in mathematics, it is absolutely rigorous, but in physics, it is usually some kind of an inference that we make. We wait for an experiment to come and say this is wrong, and then we start hunting for another result or a theorem or a not a theorem, maybe another result which will tell us a new law of physics. Okay, this is how it goes. So this, I believe, is very accessible to students, and something that I have talked about to students in my university. We have a course called mathematical reasoning. So this is something that I use to tell them what it means to reason in mathematics. But I'm not a mathematician. I'm a physicist by training, but I enjoy learning and talking about mathematics. So this will be a talk for about 45 minutes, and subsequently it will be open for a discussion, and I'll be happy to answer questions that you have. So the talk will be having a few sections, starting with an introduction, then a plausibility argument as to why the so-called Pick's theorem could be true. Then we will have a brief introduction to the method of induction, and we will actually use this method of induction to prove Pick's theorem. So this is roughly the way it's going to go. And if there is time at the end, I will show you two applications of Pick's theorem in some problems in mathematics. Okay. So who is this Pick? His full name is George Alexander Pick. So he lived from 1859 to 1942. And he is very well known in complex analysis. Therein he gave a theorem, he proved a theorem which tells us how to interpolate, given a set of points on the unit disk, a polynomial which will actually pass through those points. Okay, and in the context, he also ended up developing what's known as Pick matrix. And so he is very well known. It's a very well known name in complex analysis. But he also wrote down something called Pick's theorem in the context of lattice polygons. We will talk about what a lattice polygon is a bit later. And this itself came up in the context of proving a result in number theory. So I'm not getting into the details of that number theory part, but we will take up the result which he proved in the context of polygons. And it is very, very easy to actually construct a proof for that. So that is the reason why I chose to speak about Pick's theorem. Okay. And the unfortunate thing is he actually died in a concentration camp during World War II. He was a Jew, and therefore he was captured by Nazi, and he was sent to the one of the concentration camps, and he actually died in the camp. And he was also a friend of Albert Einstein. In fact, he headed the committee which appointed Einstein as a professor in German University at Prague. And I believe that Einstein used to discuss with them, that is with Pick, about the mathematics that was required for Einstein to develop the general theory of relativity, essentially the absolute differential calculus by Levi-Civita and others. So he was fairly well known, I should say, at that time, but unfortunately he lost his life when he was within a few weeks of taken to concentration camp. He died. Okay. So much for the person that whose result we are going to talk about. Let me move into the actual material that we want to talk about. Okay. So the object of interest in for us today is what we call as a lattice polygon. So consider a graph sheet. Okay. So we have these x-axis, y-axis, and the lines parallel to x-axis and y-axis. Let us say they are at some specific distance. A parallel line is drawn 1 centimeter away from the origin parallel to x-axis, and similarly from the away from the origin parallel to y-axis, they have got a grid. Okay. So the points where these lines intersect, they will all be now integers. So for instance, I have marked an origin here, and then 1, 0, 2, 0, 3, 0, that will give you the lattice points along the x-axis. And I have also shown you some typical points to describe the polygon that I have drawn on the graph sheet. So a polygon with the vertices on the lattice points is what we call a lattice polygon. Okay. So it turns out that we can say something interesting about these lattice polygons. So the interesting question that the PIC tried to answer in the context of proving a number theory problem is, what is the area of a lattice polygon? Remember, this is not a regular shape that we are familiar with, like a cube, a square or a triangle or trapezium, things like that. But it's rather a polygon with an arbitrary shape, and computing the area of this polygon in simple terms could be really hard. But turns out that there is a nice way to calculate the area of such polygons, provided we are able to do some counting. So let us see what that is. So before we go on to find out what could be the area, let us look at some simpler polygons that we can think of. Of course, the simplest polygon is a triangle, one which has got 3 vertices. So I'm drawing here a set of triangles. All of them have their vertices on the lattice points. Okay. So here is one, which is having vertices along these 3 points, And here is another triangle, which once again has exactly 3 vertices. Okay. And here is yet another, which looks very longish. And this is another triangle. And this is yet another one. Okay. Now, suppose you ask some school child, suppose you want to paint these triangles, which one is going to consume more paint? Okay. So I tried with quite a few students. The answer turned out to be this longish triangle. Okay. Many students, quite a number of them felt that this would probably will take more paint. And the right answer is all of them require the same amount of paint. In the sense, the area of all these triangles are exactly half unit. Okay. We'll see why is it half unit in a short while. But what I have drawn is what we call as an elementary or primitive triangle. So these are some elementary examples. Triangle is the simplest that we can think of. And these triangles that I have drawn here, I call them as primitive triangles. Primitive in the sense they have exactly 3 points on the lattice points, which will make up the vertices. But there are no other lattice points either inside or on the edges. So there are only 3 lattice points that these objects consist. So we call it as a primitive triangle. Okay, I've just shown those triangles again here. It is very easy to recognize if this has 1 centimeter and this is 1 centimeter, then the area of this triangle is half unit. Okay, it is half of the area of that square that we have drawn there. But you can also see that if you take this triangle ABD and you complete this as a right triangle as ACD, and you can easily figure out the area of ABD is nothing but the area of ACD minus area of BCD. Okay, BCD is easy to calculate because it is once again a right triangle, and therefore the area is easy to calculate. And now if you calculate the area of ABD, you will recognize it as half unit. And similarly, this longish triangle that I have here, once again, you can do exactly the same thing. Calculate the area of ACD, which is a right triangle. Subtract from that the area of BCD, which is once again a right triangle. Then you get the area of the triangle that you are looking for, namely ABD. And you will see once again, the answer is half unit. And you can do exactly the same thing with this triangle as well. And in every case, you will see that the area, so long as you have the vertices on the lattice points, and there are only 3 lattice points on the top for that object. Else on the interior or on the wedges, then the area seems to be halfway of a primitive triangle is half. How does that help us? Fine. If I take my original polygon that I showed on the very first page, what I can do is I can actually paste these kind of primitive triangles within this bigger polygon. Okay. Now the area of the bigger polygon is essentially the sum of the areas of these primitive triangles. And I know the area of a primitive triangle is half unit. So if I can count the number of primitive triangles, of course, the job is done. Number of primitive triangles into half will give me the total area of this polygon. But to actually draw these primitive triangles and then count them could be a hard task. In fact, there is no unique way. You can have a variety of ways of filling up a given polygon with the primitive triangles. So this is enough to actually calculate the area of this polygon, which is not a regular polygon, but it is still not an easy way to do that. So let us see whether there is any other way of calculating the area of this irregular polygon. So in this particular case, for the region that I showed you, it has 6 units of area because there are 12 such primitive triangles filling up that portion of that. Okay. And similarly, I have drawn here for the other portion. And once again, you can count the number of primitive triangles and the area is going to be 4 because there are 8 primitive triangles filling up this portion. So you do it for each portion, sum up all of them, you will get the area of the total, the complete polygon. Okay. Okay. Now let us draw slightly more complicated figures. That is something beyond the primitive triangle. So here I got 3 shapes. So something like a square, and then some bigger triangles on the second line, and then a square rotated by 90 degrees. And of course, I have triangle objects here. I will tell you the relationship between the objects drawn in blue and the objects drawn in red. Once again, the interesting question is, what is the area of each one of these objects that we have drawn? Okay. So now once again, I can use the same trick that I had described earlier, convert or rather fill up these objects with the primitive triangles, and you will see that the area of the objects drawn in black will have exactly 1 unit, and the area of the objects drawn in red, you will see that they will have 2 units, and the object that I have drawn in blue will have 2.5 units. Okay. Why this particular sequence? We will see the reason why we are doing this. This is the process of discovering the so-called fixed theorem. Okay. This will appear again. So if you now look at the objects in the very first line, which are, I have indicated the vertices in yellow and the edges are shown in black. Those objects exactly have 4 points on the vertices, and there is nothing else. There are no other lattice points, either on the edges or inside. Therefore, exactly 4 lattice points, and we will call these lattice points as boundary points because they lie on the boundary. So these objects have exactly 4 boundary points, and all the 4 points, of course, are lattice points. Now, if I come to the second line, there is objects drawn in red. I see that these objects also have 4 boundary points. So boundary points are the lattice points which appear on the edges of that object. But these objects, that is those which are drawn in red, also enclose another lattice point inside. So all these objects have exactly 1 lattice point inside, okay, each. And once again, by invoking our method of converting them into primitive triangles and then calculating the area, you will find the area of these red objects is 2. So remember, the area of the black ones, there is no point in the interior, but there are exactly 4 points on the edges, which we call as boundary points. The 4 boundary points give you an area of 1 unit. Here I have 4 boundary points. In addition, there is 1 interior point. So each figure has this particular feature. 4 boundary points plus 1 interior point. I find the area to be 2 units. And here, the next one, what I have done is, I have taken the objects drawn in red and extended the object so as to increase the number of boundary points. Okay. So you take this red triangle, that's what I have shown in blue here, and with a yellow line in yellow line. And you see this will exactly fit into the red triangle that I have drawn. But now I have removed that edge and then instead extended it so that I make another object which has got now 5 boundary points in the process, and that I have done for all the 3 of them. And if I once again calculate the area by what I know using the method of elementary triangles, I find the area of these objects is 2.5. So let us other way. So I start with 4 boundary points. I have an area of 1 unit. I increase the number of interior points. The points which are not on the boundary but were located within. A lattice point located within the object is what I call an interior point. When I increase the number of interior points by 1, I seem to be increasing the area by 1 unit. So same number between, what's the difference between the black figures and the red ones? The number of boundary points is the same for both, 4. And the number of interior points is 1 for the red objects, and there is no interior point for the black objects. And I find the area of the red object to be 2 units. So it tells me something like maybe when I have a boundary point, interior point, the area will increase by 1 unit. Now I have retained the number of interior points, which is 1 in all the cases, both for red and blue, but I have increased the number of boundary points by 1 unit, and I find the area is increasing by half unit. So it essentially tells me 1 interior point may be associated to 1 area, 1 unit of area increase, and 1 boundary point will give me half unit of area increase. Okay, it is something like rate at which area is going to increase as you increase these 2 kinds of points. So change in area, you can sort of rephrase it by saying change in area is equal to 1 unit, 1 area unit for per interior point, and change in area is equal to half unit per boundary point. So these are the 2 observations that we have made. Okay, and definitely these 2 observations are true for the elementary object that we have drawn so far. So, but a polygon we know has more than 2 sides. The simplest polygon we have is a triangle, so that has got 3 sides. Anything else will have more. And now I make a claim. The area of a polygon, this is a claim that I make, okay? It's not a proven statement. We have to prove this. So I have, let us say, certain number of interior points, and I know for whenever I add an interior point, I will be increasing the area by 1 unit. Therefore, it is 1 into number of interior points, okay? But the number of boundary point that I need at least 3 boundary points to make a polygon, which in our case will be a triangle. So the total number of boundary points minus 2, that tells me how many polygons I will have. If I have 3 boundary points, I will have 1 object, namely 1 elementary triangle. That's what it is, 3 minus 2, 1. Okay? And for each of those boundary points, I will have exactly half unit of area added to this. So when they use this sort of plausibility argument and say, and maybe the area of a polygon is the number of interior points, why exactly is the area by 1 unit, and b minus 2, number of boundary points minus 2 divided by 2. This 2 essentially, that 2 in the denominator comes from the fact that for each boundary point that I add, I will be increasing the area by half unit. Okay, so this is a plausibility argument, need not be true. We have only tested it for a handful of objects. Okay, you can apply this to all the objects that we have discussed so far. For instance, you take the objects shown in black here, and number of interior points is 0, number of boundary points is 4, and we already calculated the area by our elementary primitive triangle method to be 1 unit. And if I use the formula that we just wrote down, then it is a number of boundary points plus number of interior points, sorry, number of interior points plus number of boundary points minus 2 by 2, and that gives you exactly 1 unit. Now, if you take the red objects case, then of course, in this case, the number of interior points is 1. Therefore, it is 1 plus 4 minus 2 by over 2, which gives you 2. And the formula works very well for the objects drawn in blue as well. Okay. So it's possible that this works for all objects, but it needs a proof. Okay. That's the beauty of mathematics, that it is not enough if I test something for millions of objects. This still doesn't constitute a proof. We need a formal proof to say that it works for every object of, in this case, lattice polygons. So I'm planning to use what we call as method of induction. There are very many ways of proving this fixed theorem, but I will use method of induction because that is something that some of you may already be familiar. And even if you are not familiar, it is easy to learn it. Okay. So let us first start with, I'm not going to write a formal statement of the structure of a method of induction, strong case and weak, but I'm going to just give you 3 examples. And from these examples, I'm sure you will be able to make out what method of induction is all about. Okay. So I have got 1 point within the square here. Therefore, I count the number of points, which is 1. Okay. Now I make a slightly bigger square, and then I have the original one sitting here with 1 point. Then I fill up the remaining slots with points for 1 square, 1 point per square. So I have got 1 point here and 3 points here, 1 plus 3, which is 4, which I say is 2 into 2. Okay. Now let us look at the next one. So I have got this object exactly reproduced here. Now I extend it on both the sides. So I fill it up with another 5 points. And now I have the total number of points within this final square is 1 plus 3 plus 5. 1 from this object, 3 along this path, and 5 along this path. And I get 9, which is 3 into 3. Now you can see that I seem to be summing up the odd numbers, 1 plus 3, 1 plus 3 plus 5. If you draw the next one, you will find it is going to be 1 plus 3 plus 5 plus 7. And if I add the first 3 odd numbers, I seem to be getting an answer of 3 into 3. If I add the first 2 odd numbers, I seem to be getting an answer of 2 into 2. So the sum of first n odd numbers looks like is equal to the square of that n. Okay, so sum of first n odd numbers is simply n square. But of course, we have only tested it for a few. Is it really true? So I have just drawn in case you have you extend this to include n such points. So this broken things are to show that there are such extensions in between till we reach that there are n points along the vertical direction. Similarly, if you count along the horizontal direction, you have n points. Okay. Now the claim is S of n, which I call as the sum of the first n odd integers, which is 1 plus 3 plus 5 dot all the way up to 2n minus 1 is n square. So claim that I make. So we need to see whether this is indeed true. Definitely it is true for the 3 cases that we discussed. 1, 1 plus 3, 1 plus 5. In each case we found it is essentially the square of the number of odd integers that we sum up. Okay. So how do I do this? So let me assume that this S of n, whatever we propose as sum of the first n odd integers as n squared to be true. Now I construct the next object in that process. So I have one object with n points along the sides. Now I construct the next one, which will have n plus 1 objects along the side. So basically I'm looking for 1 plus 3 plus 5 all the way up to n plus 1 odd number. Previously I have assumed that it is true for n odd numbers, first n odd numbers. So I now say, assuming that it is true for first n odd numbers, let me calculate what it should be for the, if I include the next odd number. The next odd number is nothing but 2 times n plus 1 minus 1. So 2n minus 1 is the nth odd number. Therefore, 2 times n plus 1 minus 1 will be the next, that is n plus 1th odd number. And essentially that gives you this. Okay. But in this expression, I know what this quantity is, 1 plus 3 all the way up to 2n minus 1, because by assumption, this is taken to be true. So I know the minus 1 is n square. I'm adding now 2n plus 1. So plus 2 plus 1, which can be the form that we had proposed. If sum of n odd numbers is n square, if that is true, what I have shown is sum of n plus 1 odd numbers is n plus 1 the whole square. Okay, does that prove what we have assumed? Okay, what I have shown now is if it is true for the nth stage, it is definitely true for the n plus 1th stage. That's what I have shown. But I already know one. What is that? I know it is true for the first stage. Now I have already proven that what is true for the first stage, nth stage, holds for n plus 1th stage. So if it is true for the first stage, that's with 1 point, then definitely it must be true for the next stage, which is 1 plus 3. Because it is true for 3, it should be true for the next one, which is 1 plus 3 plus 5. And therefore, ad infinitum, it continues. So this is the idea behind method of induction. So you do what is known as a base case, some very elementary stuff where you know the expression is true. Then assuming that this statement is true at a certain stage, call it nth stage, you show that the n plus 1th stage follows. Since you've already shown it for an earlier case, it follows for all successive cases, and that's how it works. This is the so-called method of induction. Okay. Let me also do another example, because I have done this with figures. You can also do it with something else. Okay. Now consider rolling n dice. Okay, and each has numbers 1 to 6 printed on 6 different sides. So if you just throw one die, of course there are 6 possible totals that you will get. It could be 1, 2, or anything from 1 to 6. Now if you throw 2 dice at one shot and sum up the numbers that occur on the first die and the second die, and you ask what are the possible totals that you will get. So both the die can show up 1, 1, in which case the sum will be 2, and both can show up 6, 6, in which case the sum will be 12. So these two will set the limits, you can't exceed. But every number in between will also occur. So for instance, first die can show 4, second one can show 1, in which case the sum will be 5. So 2, 3, 4, 5, all the way up to 12 you will get. So you will have 11 possible totals. So when I throw one die, I get 6 possible totals, 1 to 6. When I throw 2 dice, I get 2 to 12. When I throw 3 dice, you will get it from 3 to 18. 3 corresponding to all the 3 of them showing 1 on each. Okay, and 18 corresponds to all the 3 showing 6 on their faces. Now, if you look at the number of possibilities, it looks like as though it fits into a pattern. So when I throw 1, which gives me 6 possible totals, I get 5 into 1 plus 1. When I throw 2 of them, I get 11 possible totals, which is 5 into 2 plus 1. When I throw 3 of them, I get 16, which is 5 into 3 plus 1. So I now make a proposal, a conjecture, if you want to call that. It's a strong word, but anyway, if you throw n dice, you will get 5 into n plus 1 totals. So this is a claim that I make. I have tested that it is definitely true for throwing 1 dice, 2, 3, but now I make a generalization and say it works, even this formula works when I throw n dice at one go and look at the possible number of totals. Is this really true? So how does method of induction help? Okay, so I make a statement that S of k be the number of totals that you get when you roll k dice. Okay, so if you use this S of k as the symbol to represent that number, then when I throw 1 die, it is S of 1, so I get 6. When I throw 2 of them, I get 11. When I throw 3 of them, I get 16. This is how it goes. Okay, and now I'm saying S of k is 5k plus 1 be true. I have tested it for a few simpler cases. Now I make a claim that it is true for an arbitrary k, which is an integer. Number of dice that I'm throwing. K is the number of dice that you are throwing. Now the question is S of k plus 1, which I claim should be 5 times k plus 1 plus 1 should be true, which is essentially 5k plus 6. Okay. Okay, now let us see how do I prove this. I have assumed that it is true for k dice. Okay. So with k dice, the minimum that you will get will be k. Remember, every die showing 1. And the maximum, of course, will be 6 times k. Each one of them showing 6 on the faces. Okay. So what are the possible total that you can have? You can have k, k plus 1, k plus 2, all the way up to 6k. Now, when you throw the k plus 1th die, of course, the minimum will be the k plus 1th die can also throw up a 1. Okay, in which case it will add to the minimum of the previous, which is in this case is k. Therefore, it will become k plus 1, giving you the minimum of k plus 1 dice is k plus 1. Okay, and when the k plus 1th dice shows 6, then that will add to the maximum that you have, because these are all positive numbers. So 6k plus 6. So that's the maximum that you have. But in the process, what I have done is, when I throw k plus 1, k will not occur at all, because the minimum will now become k plus 1. So now I will calculate the total number of possible totals when I throw k plus 1. It will start from 6k plus 1 6k plus 2 dot dot dot, and then it will continue. And of this, 6k plus 1, 6k plus 2, these are not present in the previous case, because with the k dice, the maximum was limited to k, 6k. So 6k plus 1 is a new addition to this. So how many I'm able to add that way? 1, 2, 3, 4, 5, 6. But in the process, k, which is the minimum with the k dice, is not available when I throw k plus 1, that is last. Therefore, then total number of totals for k plus 1 dice is 5k plus 1, which is what we assume. Total number from k dice minus 1, because we are missing the minimum of the k dice case, and I'm adding 6 new totals, starting from 6k plus 1 to 6k plus 6, and which gives me 5k plus 6, which I can always write as 5 into k plus 1, which fits into the form that I wrote down. If I throw n dice, the total number of possible totals is 5n plus 1, and therefore this formula that we assumed to calculate the total number of totals, okay, when I throw n dice is true. Okay, and maybe this is another example which I'm sure is something that you can try. The sum of first n natural numbers, and you know the formula is n into n plus 1 by 2, and there are various ways of proving this. So you can write 1 to n in one way and write in the reverse order n plus n minus 1, sum them up, and that's how originally it was done. But then you can also have very beautiful proof using figures, and you can also do it by induction. I have done it here. Maybe I will skip for the present because we may be running short of time, and it's easy to do. Anyway, I believe this will be shared, and so you can look at it in case you need. But anyway, these are all fairly standard stuff you will be able to find even in other textbooks. Okay. So if it's a problem, if you want a slightly trickier problem for method of induction, here is one. So square root of 2 under then followed by square root of 3, all the things under square one above the other, and you can show up to n, it will always be less than or equal to 3. It's just an exercise, don't worry about that. Okay, so let us just do a recap. So I have shown you a set of triangles here. So here is a triangle where the two sides are parallel to the grid, that is your x-axis and y-axis parallel to those two axes. And here is another triangle where you have one side parallel to the x-axis, but other two sides are not. And we have a third one where all the three sides are not parallel to the two axes that you have. That means they are not running along the grid lines that you have on the graph sheet. And we have checked in all these three cases that basic formula that we wrote down about the area of polygon will work. Okay, that's what we have, various triangles that we drew earlier. Okay. Now let me just introduce two more terms before we proceed. So when this is the polygon that I had originally drawn, but nothing sacrosanct about this. You could have drawn any other lattice polygon. So I define what is known as an internal diagonal. An internal diagonal is a straight line connecting two lattice points, but the line should lie entirely within the polygon that you have got. Okay. So here I have got two examples, this one and this one. These are internal diagonals, basically because I taken these two lattice points and connected them by a straight line, and this straight line lies entirely within the polygon. Okay. And similarly, this straight line lies entirely within the polygon. For instance, you can draw a straight line from this vertex to this vertex, and that will be an internal diagonal. Whereas what I've shown in the dashed blue line is not an internal diagonal, because it connects, of course, two vertices of the polygon, but there is some portion of this line which lies outside the polygon. Therefore, this is not an internal diagonal. So I will be using the word draw an internal diagonal. So whenever I say draw an internal diagonal, understand that it is an arbitrary, choose two arbitrary points on the lattice polygon, draw a line, and if the line lies entirely within the polygon, then you call it internal diagonal. Not that every two arbitrary vertices will allow you to draw an internal diagonal, but it is possible that you will be able to draw at least a few internal diagonals in a polygon. Okay. In a triangle, of course, you will not be, you can draw a triangle and check whether it is possible. Okay. So here is again, this is an internal diagonal, because there I had drawn all of them together. It might cause some confusion. So this is an internal diagonal, and this is an external diagonal, because these two are vertices, but the line lies outside the polygon. Therefore, this is an external diagonal. So now I make the claim that Fick's theorem is true for any triangle, which we have looked at all possible cases. Sides, both two sides parallel to two of the grid lines. One side parallel to the grid line, other two sides are not. And all the three sides not being parallel to any of the grid lines. In all the three cases, we have checked that Fick's theorem works. Now I say, let Fick's theorem be true for all polygons with less than n sides. So it works for 1, 2, 3, all the way up to, let us say, n. So I claim P of k is equal to ik plus bk minus 2 by 2. What is ik here? Ik is the number of internal points, and bk is the number of boundary points. Boundary points lie on the edges. Okay, these are the lattice points which lie on the edges. That's what I mean. So I've just shown an arbitrary polygon here, and with the points marked by red are on the boundary of this polygon, and the points which are indicate lattice points are indicated with a circle are the internal points. Okay, so O represents, the circle represents interior points, and the red dot represents boundary points. And therefore, in this case, in this particular case, you can count there are 19 interior points and 14 boundary points, and you will get an area of 25 units. You can see that it works. You can even try doing it by the elementary triangle method. Okay. Now consider a polygon P. The whatever polygon we consider, that I can take and consider that to be an arbitrary polygon. So let it be divided into two parts by an internal diagonal. So this is where I want to use an internal diagonal. And now I say, let M be the number of points on the internal diagonal other than the vertices of P. Okay, remember, every internal diagonal will consult two vertices of the polygon. I am going to avoid those 2 points and count the remaining number of points on the internal diagonal. So I represent that number by M. So now when I draw an internal diagonal, of course, the polygon will be split into 2 parts, P1 and P2, and each one of them will actually be a polygon. Okay, but what is definitely true is, when I do this, the number of points that I have will be lesser than the number of points that I have for the bigger polygon P, which I name it as P. So it definitely works for these polygons. Okay, now you may ask, it is possible that the internal diagonal can pick up more number of points, so that the number of interior boundary points could exceed that of P. Fine, in that case, you can draw another diagonal. Still, you get to a situation where the number of boundary points and the number of interior points are lesser compared to the number of boundary and interior points that you have for the bigger polygon. Okay, why do I do that? Because I have assumed that the Fick's theorem is true up to a stage. Yeah. Now I want to see whether it works for n plus 1. So any polygon that I construct must satisfy that condition. Now let us see what it means in this particular case. So I have just drawn an internal diagonal here, and I call these two partition as P1 and P2. So I1 represents the number of internal points for P1, and I2 represents the number of boundary points on P1. And the area you can calculate, it's given here. And similarly for P2, which is here, this portion is P2. You can count the number of interior points and the number of boundary points, and you can calculate the area. You sum up the area, you get it as 25, which is what we got for the original polygon. Okay, these are for specific numbers. These are not really important. We are going to prove that in general. Now, we know that M is the number of internal points of P on the diagram. Okay, those are the as far as the original polygon is concerned, these are internal points, but it will be one of the sides for the polygons P1 and P2. Now, how do I calculate the area of the smaller polygon P1? It will be the number of internal points, which is I1, plus B1 plus M minus 2 by 2. B1 is nothing but the number of points, boundary points, which are common to both P and P1. That is the boundary points of P and boundary points of P1. So that's what I call as P1. And since this internal diagonal forms another edge of the polygon P1, I have to count the number of points on the internal edge, which is M in my case by definition. Of course, -2 is what we proposed in the original formula. Therefore, this is essentially Fick's theorem applied to a polygon where the number of internal points and boundary points are lesser than the original. Okay, therefore it works. And similarly for P2, number of internal points plus number of boundary points, which is B2 plus M. These are the number of boundary points on P2 minus 2 by 2. So I have got the areas of P1 and P2 written in terms of their internal and boundary points. But area of P is nothing but area of P1 plus P2 because these are non-overlapping polygons. So as far as the original polygon P is concerned, the number of boundary points will be B1 plus B2 minus 2. Why that minus 2? If you go back, I'm just showing it as an example, but it's easy to visualize. This point, these 2 points, which are the edges or the of the segment, the internal diagonal segment, the endpoints are counted both for P1 and P2. Okay, therefore I am counting it twice, and there are 2 such points counted twice. Therefore, I have to subtract out that additional overcounting that I have done. That is why that -2 when I calculate the number of internal points for P. I think I should go to the previous page. Okay, and the number of internal points is I1 plus I2 plus M, because I1 is the number of internal points for the polygon P1, I2 is the number of internal points for the polygon P2, but the points on the internal diagonal is a boundary point as far as P is concerned. Therefore, I should add that if I am considering the polygon P. Therefore, the number of internal points for P is I1 plus I2 plus M. So what is it that we are trying to do? We are trying to do everything about P in terms of what I know about P1 and P2. So that's the purpose here. And therefore, the area of P, of course, is the sum of the areas of P1 and P2. So now we will plug in all those things here. Therefore, what I have written down here is the area of P1, and what I have here is area of P2. So I just regroup them. I1 plus I2, there is an M by 2 here and an M by 2 here, which gives me M plus B1 plus B2 minus 4. Minus 4, I'm going to write it as -2, which gives me I1 plus I2 plus M, which I know is the number of internal points for the polygon P. B1 plus B2 minus 2 is the number of boundary points. Remember, this -2 is basically because I'm counting those 2 edges, final endpoints of the internal diagonal twice. And that is why I have to subtract that by 2 to get the actual number of boundary points for P. Of course, this -2 is in the right position to give me what I need. Therefore, it is I plus B minus 2 by 2. What I have shown is I have assumed that the expression that we wrote down for the area of a lattice polygon for all number of internal and boundary points lesser than whatever I have here, I and B, I have assumed that it's true. And if that is true in all those cases, it must necessarily be true for the polygon that I am considering. But I have already checked that it is true for the polygon with the 3 lattice points, and I have checked it for a polygon with the 3 lattice points and 1 boundary point. Therefore, now it works for any polygon with any number of lattice points. That is, number of, you can apportion it the way you want it for boundary points and internal points. And that proves that Fick's theorem is true for, or the area for a lattice polygon is simply number of internal points plus number of boundary points reduced by 2 divided by 2. That's it. Do I have time to go to some applications, or I can skip? So, okay, let me, I think it is 11:45 already. I have exceeded by a few minutes, but let me just tell you the problems you can try on your own. For instance, you can ask a question, is it possible to draw an equilateral triangle where the vertices are on the lattice points? Okay, you can construct a proof without invoking Fick's theorem, but with the Fick's theorem, it is very easy because you know the area of that triangle. and you can easily work out the area of an equilateral triangle, and you will see that it will lead to a contradiction in the sense that you will be able to write an irrational number as a ratio of two integers, and therefore Fick's theorem will actually help you to show that you cannot draw an equilateral triangle on with vertices on the lattice points. Okay. The other one, which has some historical connection to why Fick's did, has something to do with what we call as a Fourier sequence. Fourier sequence is essentially, okay, I have given you the definition of Fourier sequence here. It is better to read it from there. The sequence of all reduced fractions with the denominator not exceeding n, listed in ascending order, is called Fourier sequence. Okay. So let me just look at two examples. If I want a Fourier sequence of order 2, I will have 0, 1 by 2, 1. So the denominator never exceeds 2. And it should be arranged in ascending order. If I look at a Fourier sequence of order 3, it will be 0, 1 by 3, 1 by 2, 2 by 3, 1. Okay. So none of these fractions will have denominator exceeding 3. Okay. And these are all fractions between 0 and 1. And these fractions have to be arranged in ascending order. And similarly, you can do for 4. What is interesting is when the moment you do arrange them in ascending order, 1 into 1 minus 4 into 0, the difference is 1. And take these two. 4 into 1 minus 3, 1, the difference is 1. Or you can take these two. 3 into 1 minus 2 into 1, the difference is 1. Or 4 into 2, 3 into 3 minus 4 into 2, the difference is 1. Okay. So if you want to show that in a Fourier sequence, when you cross multiply these two terms and take the difference should always be 1, is easily proven using Fick's theorem. So that's all that I want to say. And it's very nice construction. It was, if I'm right, it was put out by Steenhaus in his book on mathematical snapshots. Later on was Polio also did something on this as a pedagogical paper. Very interesting and easy to read. So I leave it. I will not get into the details. Before I leave, let me just tell you, where did I read about this when I was in school? So I do not know whether these books are available now. A book by U.A. Shashkin, The Euler Characteristic. So it is one of the books in what is called as Little Mathematics Library from Mir Publishers. I'm not sure whether these things are available now. And of course, these results are available in many other books now. In case you can lay your hands on this book, it's very good. It talks a lot more, starting with the Euler characteristic. And in this book, Fick's theorem is derived as a application of Euler characteristic. Okay. And what we have not used Euler characteristic at all. Instead, we took the route of proof by induction. But if you can get hold of this book, it's a very nice book. In fact, any book in that series is wonderful, but this is also a nice book. And before I thank organizers, let me thank the participants for their participation. And in case you have some doubts and you want to write to me, here is my email ID, sivakumar.srinivasan@krea.edu. Thank you very much.
Thank you, Shiva sir. Participants, we will take a couple of
minutes. Can I just show one more page, Deepak?
Yes, sir. We have time. You can go ahead. You will have to share your screen again.
Yeah. So as an extension, if you want to spend your time during these holidays, because I know you can't go out, you can see, assume that these objects are lattice polygons drawn with the vertices on lattice. Find out whether you can calculate the areas of these objects using that kind of a formula. So this is essentially a polygon with a hole. So assume that this rectangle is a polygon. It can be of any shape, and inside it there is a hole. So this region is removed. If I remove this region, can I write a simple expression like the way we wrote for a polygon without holes? It is possible to do it. Therefore, I leave it as an exercise to you. It's a very interesting exercise to do. Yeah. There I stop. Thank you very much. If it had become a bit intense, I'm sorry, but this is a very beautiful subject. Let me tell you, don't estimate the beauty of the subject based on my lecture.
Thank you very much, Professor Sivakumar. Can you take some questions now? I think Deepak will.
Yes,
absolutely.
Before we take the questions, I'd request the participants to share their feedback. It's a very short number of questions. I'll paste the link in the chat box. Please share it. Let's pause for around 1 minute, 1.5 minutes. Then one more form will be shared where you can post your questions, type your questions, what you want to ask Sivakumar sir. Okay, I'm sending the link now on the chat box. Thanks everyone for sharing your feedback. Now I've pasted the Q&A form. You can ask your questions, type your questions on that, and we will share it with Sivakumar. Sivakumar sir, a couple of minutes as the questions come. I will compile it and share my Microsoft Word with you.
The number of participants is very less. Is it possible to actually ask them to unmute and ask? Could be faster. Is it permitted? I don't know.
Shiva, the number of participants, I'm not fully understood why we didn't have so many. I think all of them did go to schools. I would like to ask the reason. I will find out.
Okay. No, I'm just asking Deepak whether they can unmute and ask, because the number is not very high.
Correct. No, the talk can be, it has been recorded. So it is already, we will upload it in the CMI website.
Mani sir, Sivakumar sir is asking, can the participants speak and ask the questions instead of typing them?
Sure.
Okay, I will unmute everyone. Okay, I've enabled the unmute option. If anybody wants to ask the question, they can unmute and raise their questions. And on YouTube live stream, they can type their questions, which I'll paste it on the screen and share it with Sivakumar sir.
Yeah, I have it up.
Yeah, go ahead.
Yeah. A circle also has lattice points, so can we use the same application and find the area of a circle? Or will the formula change?
Yeah. Yeah, you can, but it will be an approximation. In the sense, you have to draw squares so that it closely approximated both from inside and outside. Yeah, because circle, if you can draw a circle, but it will not actually, remember, the circle is not a polygon. Right?
Yeah.
So you need straight edges for this. And if you remember, our basic unit is actually a triangle, elementary primitive triangle whose area is half unit. So you can actually fill up a circle with primitive triangles and calculate the area approximately. And in the limit of the triangle size becoming smaller and smaller, you can do. See, my grid size need not be 1 centimeter by 1 centimeter. It can be half centimeter by half centimeter. So that whatever a unit I have for that triangle on a half centimeter grid, I will call that as half unit. Okay, you can later on always scale it up by the factor that you have. But you can make it smaller and smaller and do, yes. But it will be an approximation.
Will it work in case of three-dimensional figures also, or is it only apply for 2D?
No, in 3D it doesn't work. In fact, there is a very famous construction by Reeve, who actually constructed a counter example for this. Of course, in 3D, we will be calculating the volume, not the area. So it doesn't work for 3D. There are classes of objects for which we works. For instance, for objects which are in the shape of a prism, objects like a cube, cuboid, those things it works, but not for an arbitrary object. In fact, we know a counter example.
Thank you.
Sir, I'm Tinetra from the Shram Academy. I have a doubt, sir. Is this Pick's theorem applicable only for polygons that have lattice vertices?
Yes, that is true. It is true only for a polygon whose vertices are on the lattices of a grid.
Yes, sir.
That's
Thank
true.
So there's one question from the form, which is there an alternative to the Pick's theorem? Is there an alternative to the Pick's theorem?
You are cutting in and out, Deepak. I'm not able to hear you clearly.
Can you hear me now? Is there an alternative to the Pick's theorem?
Better, but still your voice.
Alternative
will. Alternative, I do not know what of course, remember, Pick's theorem is to give you exact area for lattice polygons. Okay. If you are asking whether we can write it, the area in terms of in some other form, not as a sum of internal and exterior points, internal points and boundary points, I have not come across anything like that. I think using internal points and boundary points, this seems to be the only way we can write the area. Otherwise, whatever I told you earlier, you can calculate you can count the number of primitive triangles, which you can always do for any polygon. So half into number of primitive triangles will give you that area. But that's very cumbersome. So this, in my opinion, is simpler. And these are the only two things I know of. Yeah.
I have another doubt.
Yeah.
In the examples that you gave, most of the area was only like all the areas of the polygons were differed, but like it was either a whole number or it was something followed by half. So would this only work in the case of, rational? Will it give the area in terms of a rational number, or can it also be in terms of an irrational number?
So this is, in fact, the last problem that I showed you, that an equilateral triangle cannot be drawn on lattice. That will automatically tell you that whenever you have a lattice polygon, remember, there is a basic unit of area here. If the basic unit of area is 1, then the area of any lattice polygon will be a rational. In fact, they will differ either by half or 1, nothing more.
Okay, got it. Thank you.
In terms of that basic unit area, which in my case, I have taken it as 1 unit.
Thank you, sir. Is there a way to find the lattice points of the polygons, or whichever figure that we get?
From the area formula?
To apply Pick's theorem, the vertices need to be lattice vertices, right? So for that, how do we find the lattice point of each figure?
Oh, I have assumed that the polygon is already drawn on a graph sheet. And the polygon has its vertices on the lattice point. Yeah.
So in tests or exams, if we get questions which gives us the dimensions of the figure, can we also plot it in the graph and do the same? Or
yeah, you can in principle figure out that whether it will actually be a polygon on the lattice point or not, but that will actually involve doing a lot of work. But you can do, you are right, you can do. If you give me all the lengths of edges, I can tell you whether.
Okay, yeah, thank you.
Sivakumar sir, one more question from the Google form. I'll read it out. Would this be applicable also for cyclic polygons?
What is a cyclic polygon?
That has not been mentioned.
I think the person who asked the question meant a cyclic polygon is a polygon whose vertices would be inscribed on the circumference of a circle.
I mean, my understanding is a polygon which can be put within a circle, whose vertices will touch the circumference of a circle. It depends on how many such polygons, how many sides you have. Yeah, but it's possible that, for instance, I can think of a square and I can draw a circle around that, in which case square will be inscribed in that circle. It will be fitting into a definition of cyclic polygon, but no, not in general.
We'll wait one more minute, Sivakumar sir, just in case any questions pop up, and then.
Yeah.
So if there are no further questions, before we conclude, I just want to ask one question. If I take a spherical surface, can this Fick's theorem be extended there? Like a ball?
No, it doesn't work.
Not possible.
Yeah.
I see.
You can't, you won't.
Okay. Okay, thank you very much. It was a very nice talk. I want this talk certainly to be transmitted to many school students. They should be aware of this method of functioning, of using induction, and then also using the basic calculations which you showed very nicely with examples. Thank you. Thank you again.
Sivakumar sir, one more doubt from Mr. Charanjit. He has raised his hand.
Please go ahead.
Will the formula change if there's like a hole in the polygon that we plot in the graph?
Yeah, you need an additional term. That is why I gave it as an example. I mean, as an exercise. You can try. Yeah, if there is a hole, it will change. But it is not difficult to calculate, because now you can calculate the area of the full polygon without the hole minus the area of the hole. So now you will be able to sort of rearrange them in a nice form. So now it's okay. Put it this way. Now you ask, how will I count the boundary points and interior points of the polygon with a hole? It is essentially that.
Can
so
you
the
also
moment you
polygon into different parts instead of considering the hole and then add up the area?
The other way, you take the full polygon without a hole, calculate the area. You know Fick's theorem works. Now you consider only the hole. For a hole also Fick's theorem works, because that hole also should be again in the lattice polygon shape. So the difference of these two will give you the area of the polygon with a hole. Now you will be able to sort of rearrange this formula so that it will tell you how to count the number of interior points and boundary points for the polygon with a hole. Yeah.
Okay, thank you, sir.
So it's not very difficult. You try. It's a very nice exercise to do.
Thank you, sir.
I think that is the end of the questions, Sivakumar sir.
Oh, thank you very much. Thank everyone for their patience and subsequent discussions.
Thanks. Bye.
Thank you. Bye.
Thank you, sir.
Time.
Thank you, sir.
Anytime.
Thank you, sir.
Anytime.